Everyone, I left off in class with the first problem on calorimetry with no phase changes, so I just want to review that theory a little bit, and then I will pick up again with the examples. So in calorimetry problems, many substances, at least two or more, are put into an isolated container and allowed to come to thermal equilibrium. The substances will exchange energy until they all arrive at the same final temperature. At this point, this is called the equilibrium temperature, and energy transfer no longer occurs. So if the system is isolated, there can be no energy transfer into or out of the system. And in that case, the total energy change of the system has to be zero. So if we add up the energy change term for each question, and we have a Q value for each substance, the sum of all of those Q values should add to zero. So it looks like this, and if there's no phase changes, then there's one Q value for each substance. And we can write Q equals mc delta T. M is the mass in kilograms. Delta T is the change in temperature, either in degrees Celsius or Kelvin. And C is the specific heat in joules per kilogram degrees Celsius. The specific heat is specific to the material, and it gives us the amount of energy required to increase the temperature of 1 kilogram of the substance by 1 degree Celsius. You can find those in a table generally for the question, and I'll give them to you here as we work through the examples. Okay, so I'm going to start by looking at the first example, which is number 9 in my lecture slides. So we have a 750 gram aluminum pan is removed from the stove and plunged into a sink filled with 10 liters of water at 20 degrees Celsius. The water warms to 24 degrees. What is the initial temperature of the pan? So, like always, we can start by listing our known information. So I have the mass of aluminum is 0.750 kilograms. Final temperature of the aluminum as well as the water is 24 degrees since they have to be the same. So we're looking for that initial temperature of the aluminum. Then I have the mass of water, which is 10 liters, and I showed you how 1 liter of water weighs 1 kilogram. So that means we have 10 kilograms of water. The initial temperature of the water is at 20 degrees and the final temperature at 24 degrees. Okay, so then we need the specific heats for each substance. So I have 4,186 joules per kilogram degrees Celsius for water and 900 joules per kilogram degrees Celsius for aluminum. All right, so you can pause that if you like. I've listed the given information there. Now I'm going to set up the heat transfer equation. So I'll have Q aluminum plus Q water equals 0. And for each one, I'm going to fill in Q equals mc delta T. So this will be M aluminum, C aluminum, T minus T naught aluminum plus M water, C water, T minus T naught water. Maybe I'll try like that. Okay. Equals 0. So I've got my transfer equation there, and we're going to solve for the unknown, which is T naught AL, so just this value here. So I'll just rearrange that, and then we can solve. Okay, so I'll have MAL, CAL, T minus M aluminum, C aluminum, T naught aluminum, plus M water, C water, delta T for water equals 0. And then when I rearrange, I get T naught for aluminum equals M water, C water, delta T water, plus the mass of aluminum, C aluminum, T, all over M aluminum, C aluminum. Okay, so there we go. That is the final energy transfer equation there, rearranged for the unknown. And at this point, I'll just plug in the numbers and then we can solve. So this will be um, 10 kilograms, 4,186 joules per kilogram, degrees Celsius, 4 degrees increase for water, plus 0.750 kilograms, 900 joules per kilogram degrees Celsius, times 24 degrees, all over 0.75 kilograms, times 900. And that should give a final temperature of 272 Fahrenheit. Okay, so I'll hold that up for a second. So I've just plugged in the numbers at the end, and then we get the final temperature here. And that's really quite hot, actually. So that's about 520 Fahrenheit, right? So if that helps you. Okay, so let's keep going. Now I'll go on to example 10. And in example 10, I have 200 grams of an unknown material is heated to 90 degrees, then dropped into 50 grams of water at 20 degrees in an insulated container. The water temperature rises to 27 degrees Celsius, then rises no further. Identify the metal from its specific heat. So let's call that unknown metal X, and we have X, and then we have water. Okay, so C water, 4,186 joules per kilogram degrees Celsius. The mass of water is 0.05 kilograms. Initial temperature of water, 27, and that's going to 27.7 degrees Celsius. And then I have unknown substance X, 0.2 kilograms, with initial temperature 90, and final temperature 27.7 degrees. And we're looking for C. So the unknown specific heat for that unknown substance is our unknown. And then we can compare to a table of known specific heats to identify what it is. All right, so let's write out that equation. We have Qx plus Qw equals 0. And then mCx, T minus T naught X, plus M water, C water, T minus T naught water equals 0. Okay, so I'm just going to arrange this equation to solve for this unknown specific heat. Cx equals negative mass of water, C water, T minus T naught water, over M, T minus T naught X. And at this point, we can plug in the numbers, so we're almost done. Okay, so that is negative 0.05 kilograms times 4,186 joules per kilogram degrees Celsius times 7.7 degrees is the temperature change for water over 0.2 kilograms times 27.7 minus 90 for the unknown substance, which ends up giving me 129.3 joules per kilogram, degrees Celsius. And if you have a look at the specific heat table, find 129.3 and it looks like that might be lead. So a good guess for that is lead.